Good morning, Dallas. Good morning, America. Good afternoon, Europe. I could say, and good evening, Asia. And wherever you are, whichever part of the world you are watching this show, the Global Electronics Talk Show of every Friday with your host Rajiv Kulkarni. Here we are today, the April 18th, 2025. Central Standard Time of US is 9:30 a.m. and in India it's 8 p.m. right now. Why I talk about India is we have the guest from India, that is from Bangalore, which is supposedly the Silicon Valley of India. And as Bangalore is known as the tech hub of India right now, and as you all know that we have a lot of skilled manpower from Bangalore, India. And today's guest is also he's a technology expert from India. He has vast experience in the design, in the manufacturing, in the testing, and so and so forth. And also, he is an IPC trainer, and plus, he is the current Surface Mount Technology Association. In short, it's SMTA, president of Indian chapter. Ladies and gentlemen, today's topic is densification part 3. Yes, densification in electronics refers to the process of increasing the density of components, circuits, or systems on a given surface area or volume. This is driven by the need for smaller, lighter, and more powerful electronic devices. As we all know, the circuits are getting more and more dense due to the demand of features, whether it can be automotive, whether it can be consumer electronics, whether it can be the telecom structure, data center. The data center is becoming a huge exploding market in the world, I would say, on a global basis, because the data transferred between the receiver and the transmitter is humongous, and also everybody wants to collect the data on a cloud server. So those days are gone where we used to use a lot of papers to store the data in a hard copy and so on and so forth. Also external hard drive and so on and so forth. It does happen even today also, but it's also something called cloud server we have, where a humongous data being collected. And because of that, the circuit designs have become very, very dense, and the topic of densification falls into that category. And today's topic is basically co-optimization of densification in the electronics manufacturing. Today we have Mr. Ambaprasad, who is a technology consultant based out in Bangalore, India. And as I mentioned, he's gave you a brief profile about him. And we are going to welcome him, and we are going to talk about the densification in the electronics manufacturing and with Mr. Ambaprasad. Mr. Ambaprasad, welcome back to the show. How are you today?
Yeah, doing well. And you said data center. I think that is the data center is the one which is driving the technology today. Yeah, we can
Yeah.
go forward.
Yes, yes, yes. And excuse me, as I mentioned, today we are going to discuss this, and Amba Prasad has prepared a fantastic presentation of this, and so I'm going to walk through those presentation, and Amba Prasad will describe or explain each, the relevant topics slides with you all. And if you have any questions, please don't hesitate to put those questions in the YouTube link if you're watching, and we will be very happy to answer those right here. Amba, let's start. The appendix, the slide is here. The agenda slide is here.
Agenda slide. So we stopped at assembly issues in the last episode. Now maybe we can continue from that so that people have a continuity in the chain. Then we can go to page 19. That's where we stopped.
This is the page we stopped. Yeah, we can start.
This is what we were telling, just an example, component which is 0 to 0, 1 or less. How we told we do the placement with respect to the solder paste, and then it is centered with the solder paste, and due to the reflow and capillary action, the solder paste pulls back the component to the component pads. So this is done purely by AI machines, and they give a feedback either to solder paste, printing, or design, telling where the problem is, and through IPC CFX protocol. And yeah, this is not a usual CAD output. Actually, the CAD output, which is optimized to align with the solder paste. Okay,
Okay.
go to the next page, please. So sometime back, about hardly 5 minutes back, you were telling about data center. When we talk of data center, we talk of amount of data transferred, which we are talking as a bandwidth, which is on the y-axis. And you use some energy to transfer data. That is energy is so many picojoules per transfer a bit of data, and how much you can transfer, what is the length you are transferring. And here we are talking of 0.01 micron, zero point 0.1 micron, and then it goes to, no, it's meters actually, 0.01
Yeah.
meters, 0.1
Meters.
meter,
Yeah.
1 meter, 10 meter. Why 10 meter? Today, data
Yeah.
centers can be 10 meter apart. The shelves can be 10 meter apart. Then 100 meter. In the same, what we call as a central office, it can be 100 meter between two cards. And then 1,000 meter and above. It can be within the city, or then you can see here the traditional copper interconnects, then RF and microwave, integrated photonics, hope patched package optics, and then optical fiber. So this is how it just goes. The technology is this is the interconnection scaling which is happening. Yeah,
Excellent.
we can go to next slide now. So when we design for yeah, previous page. The
Yeah.
previous page. Yeah, stop there. So
No,
when
this one,
we
right?
do
Yeah.
design, the
Yeah.
this one, correct. So when we do the design, the days of doing a design and giving it to PCB fabrication and giving it to manufacturing and test are over. Now we have to do what is called as a co-design. And when you do, you have to do co-optimization. Otherwise, there should be optimization in design, or in material, or in manufacturing methodology. So system technology co-optimization, an advanced approach where semiconductor and your interconnection, as well as software, system integration, component selection, everything is optimized almost on the fly. People give a 360-degree feedback, and either the component or the interconnection or even the software, they have to do some optimization. Otherwise, everything cannot fit into one design. So
Yeah.
everybody cannot have their say. They have to co-design and co-optimize. Go to the next page, please. Okay. Here, I'm giving a slight twist. Once you define a system, you generally jump into design. That's what it used to be earlier. But here I'm showing with a twist. Here I'm telling whether my system can be manufactured or not. And then we start designing. Okay. So that's why I just did a twist. Design I'm pushing to the third step. Before that, we do manufacturing feasibility and all. Manufacturing technology co-optimization. Manufacturing technology co-optimization in packaging design. This is not a design rule or something. This is a culture. This is a
Yeah.
company culture. This is an individual culture. Okay. It's a culture. Material selection, use innovative material, process optimization. Even before the design starts, you know where the board is being built, and design integration. Then cost reduction. The cost reduction, maybe we may spend a lot of time in design, but when we produce so many boards, maybe they are produced at a cheaper cost.
Yeah.
And reliability. Reliability is the final, that there is no compromise on reliability. So then again, there are some soft issues like signal integrity, power integrity, and thermal management.
Great.
Yeah. So then, technically speaking, design should come first. But why I told is whatever we design, you give designers keep on designing, they keep on designing. They never release actually. they never come out of that. So there should be a target for them, then only they release. That's why I told manufacturing first. It should be driven. Okay. Then design technology co-optimization. Again, this is a culture. Companies have their own DNAs. Individuals have their own DNAs. The methodology right now used in semiconductor, but since in the last episode I told high density, ultra high density, the semiconductor packaging technologies will come into PCB workflows. That's why I took from there. A methodology right now used in semiconductor manufacturing to optimize both design and process technology together. It's a 360-degree loop back. Okay, focusing on improving key metrics like performance, power efficiency, density, transistor density, and cost. These are the optimization. DTCO involves close collaboration between design and process teams to ensure that innovations in one area complement the other. So basically, as far as I know, there are very few companies which they do design as well as the fabrication under their management. Otherwise, generally it is what we call as it is subcontracted. Somebody else will do the manufacturing. That's why there should be a close interaction and there should be a feedback coming constantly. So design is co-optimized, or even manufacturing is co-optimized for design. That is design technology co-optimization. Then go to the
Excellent.
next page, please. Yeah, this is the typical workflow. In a GTCO workflow, it involves optimizing both design and manufacturing processes to achieve better performance, power efficiency, and cost effectiveness through material selection, design rule development. The design rules, the semiconductor companies will give PDKs, process design kits, and ADKs, assembly design kits, that is built into the design rules. And simulation and modeling, this keeps go on and on and on. It is not that people will do almost, they keep doing simultaneously. Simulation and modeling, what if scenarios, if you do any change, then you have to remodel it again. Prototyping, you build your system, create prototypes to test the integration of design goals, manufacturing, and refine design-based performance matrices. Okay, so that when we go for the next run, we get a better yield. Manufacturing process optimization, collaborative with manufacturing teams to ensure the process supports densification without compromising on reliability. So reliability cannot be compromised. When it comes to reliability, either manufacturing or design, they have to take a step back. And that's what it is. And generally, people, they don't want to go to the cutting edge. They work at almost at 80 to 85% densification goals. They don't go full 9 yards. They stop at somewhere.
Correct.
And so that, there is some elbow room for process adjustments. Then validation and testing. Conduct rigorous testing to validate the design and ensure it meets the desired specification. So as the density becomes more, the gap between the nodes becomes very less. The gap between the component parts becomes very less. Sometimes components are embedded within the PCB. When we say test, it is automatic test. Maybe AOI and AXI and functional test. Next page,
Excellent.
please. Yeah.
Let's take a quick break and we will come back. Good morning, good afternoon, good evening. Welcome to the Global Electronics Friday Talk Show with your host Rajiv Kulkarni. And we today we have the topic of densification on the electronics, actually co-optimization of densification in electronics manufacturing. And this is the part 3 of densification topic. And all the topics have been covered by Mr. Ambaprasad, who is a technology consultant based out in Bangalore in India. Every Friday, we bring Global Electronics Talk Show to bring electronics knowledge and electronics sharing and so on and so forth. If you have any topics, you can definitely get in touch with us, and we will be more than happy to bring that topic and discuss with you. You can send questions in the YouTube link, and we'll be happy to answer during our show. And today's show is on densification. We'll be continuing after this. We had this small break. Let's continue the discussion. Mr. Ambaprasad, welcome back to the show. And I will share the screen again and continue with the presentation. Yeah. Can you see?
Yeah.
Okay.
So we were discussing about workflows. Here I'm showing a few differences. There can be many, but these are the key ones. Difference between BAU model and DTCO workflow. BAU means business as usual. You know, there are some technologies where people still want to do a business on as usual model. They have their own, you know,
Way of
compulsions to do
conducting
that.
business. Yeah.
They do that. Low-end technology. I mean, as we discussed last time, still Through is thriving and giving a big fight for all these technologies. That goes on and on. But however, when we go for a densification, design flow in earlier model was sequential, but in DTCO it is integrated and iterative. You get the feedback on the fly.
Okay.
And manufacturing considerations in a BAU model, it is an afterthought. But that's why I showed manufacturing technology co-optimization first, and then I went into design co-optimization.
Design.
Considered early in the design and continuously. Collaboration, we cannot say our design is a secret or something. Through a proper NDA and responsible sharing, the design has to be shared very early and feedback collected. Then optimization focus. Optimization is not just a DRC or something. It is a work culture. It has to be built into the system. It is a company culture. Okay. Handling of complexity. Business as usual can struggle with highly complex embedded designs. But here you can even put components, embedded components. In fact, we can put waveguides within the PCB. We can put optical fibers within the PCB and backplanes, power supplies within the PCB. This is really state of the art now. It is not future. It is already happening. Time to market. Business as usual is very longer, but DTCO is, in DTCO, even before you build your design is sold. That brings a heavy pressure on the design team, but that's what it is. You know very well the manufacturing goals and marketing goals even before the design starts. So that's the key difference here. Cost. Cost of traditional design is potentially higher due to late stage issue resolution. Like it is cheaper to design, but very costly to produce. They use more material actually. They use more solder, more wires, more PCB material, more area, more volume. Data centers, they want to pack as many racks as possible in one floor. You should take the overall cost and not just a component cost. Then the reliability may have a lower initial reliability due to unaddressed issues, but higher due to early identification. Because all the time when we talk of testing, we talk of testing of a PCB and assembly. In DTCO, even components will come pre-tested. Your components, your connector, and your PCB laminate, everything is pre-tested before it comes to the supply chain. So that's the advantage you have. Next slide, please.
Oh, something happened. Wait 1 second.
Yeah.
Yeah. Yeah. You can continue
No, the
sharing the
slide is not
slide.
visible.
Yeah.
No, we have only 2 more slides. That way, no problem.
Right. Right. Okay.
We have enough time.
Here you go.
Yeah, I can go for a full screen.
Yeah.
So the difference between regular and densification design methodologies, feature size decreases. So regular designs, complexity is generally low complexity. Again, this is exact opposite actually. This is almost
Mm.
180-degree apart. So generally higher due to substrate and solder ball attachment, even wire bonding, and people do sort of compression mounting and all. Common assembly methods, DIP, PGA, SOIC, it can be hand assembled or even low end machines, but here we have to go for a high end machines. Then required equipment, standard soldering pick and place. But here what happens, the AI takes over. Automatic
Mm.
intelligence, it decides the workflow. And in fact, stencil printing may not be there. They may have to go for a jet printing. These are the few examples we are giving. Relative cost per component often lower in regular designs, but it is very costly in densification designs because here, in fact, in PCB technology, you pay money to remove copper.
Mm.
More integration we do, we pay more money for that.
And
And
also, when
relative
it comes to densification method, it more goes into the surface mount technology
It goes to
rather
surface
than.
mount, it goes to ultra high density. In fact,
Mm.
IEEE is calling as heterogeneous integration. They have the semiconductor people, they have their own problems because of Moore's laws slowing down. See, but here basically the semiconductor disciplines will come into the assembly houses. And in fact, cleanliness is very much important.
Mm.
Cleanliness, cleaning the circuits, maybe some other expert can conduct a session in global electronics. It is not an issue. The cleanliness is very important, and your assembly room and even testing has to be dust proof. I mean, it's almost like a semiconductor room. Machine ESD is the biggest threat. It has to be ESD proof. So there are a lot of it's a huge investment actually. And
Yeah,
again, relative cost. Yeah.
in fact, I want to make a comment when you said cleanliness topic on global electronics. It has been done 2 times on
Yeah,
global
yeah, yeah.
electronics on cleaning of PCB or or the assembly, right? By Dr. Adam and Adam Klett, who works for Kaizen,
Adam
and
Cleat.
Adam Cleat, yeah, and he works for the Kaizen, and yeah, and people can definitely watch that episode. It is available on the YouTube channel anytime. So please continue.
See, what happens is when we say densification, these are all very low profile components and low standoff components. Below the
Right.
component, between the component underbelly and the PCB surface, the gap is very less. It is a few microns actually. So that's why the cleanliness becomes important. There should be no debris due to assembly or whatever. And yeah, that's why the cleanliness is very important. And again, the machine related ESD, as long as there are two separate metals are there, you always have a
Mm.
threat of electromigration, which we covered some time back, and also ESD induced, which transfer to as electrostatic overstress on the functionality test. UOS failures will happen. So this is a very major threat, and the entire assembly line has to shut down, and they have to clean it up and again recalibrate and come back. So this is a major. Everybody cannot do it. It requires a very big investment and very a big work culture and things like that. And the relative cost assembly per component, a regular design is cheaper, but per component it is moderate to higher. But a system-wise cost, it comes down in
Mm.
densification models. What could have been a one PCB can be a one small module or a chip. So that is where you save. And I have one interesting slide on this. Maybe in the next episode or sometime we can
Yeah,
just
we can do that. Yeah.
yeah, yeah. So
Okay.
densification not only caught the attraction of technocrats and technical experts, also governments are jumping into it. This is as on February, US government started technology thrust area. Uh, they call it as a semiconductor manufacturing thrust area and packaging, assembly, and test thrust areas. And these two are interrelated. Okay. I mean, you cannot design what you cannot manufacture, and whatever comes as a design, you cannot manufacture. I mean, you have to give a feedback. This feedback loop happens to be a digital twin that is in the middle, sitting very smartly. The digital twin, in fact, a lot of EDA companies are investing heavily on digital twins, and data gets transferred through a secured IPC CFX protocol. And yeah, there are a lot of what if scenarios and yield results, and people become process experts actually. The Six Sigma, what we call, okay, it is actually 4.5 sigma, but people still call Six Sigma. So that comes into your play. Even the designers and the assembly, if not the assembly operators, the assembly managers, the program managers who do the assembly programming, they should be addressing 4.5 sigma. All this comes into a big role. There are so many packaging component materials, technological optimization, packaging assembly, packaging testing. Actually, whatever I covered in the previous slides, this diagram is showing very neatly. Yeah, this is the future. Like companies are investing heavily on this. Even Europe is investing heavily. Lot of institutions are involved. Even SEMI, IPC, JEDEC, SMTA, Surface Mount Technology Association, they are investing heavily on these technologies. So next slide,
Excellent.
please. Yeah.
Excellent.
Yeah, and I think this is the last slide we have.
Yeah,
The
that's
role of
right.
standards and design guidelines. So there is a difference between a design guideline and a standard. So design guideline is specific to one particular product or a one particular company or a chipset. Standard means it is a universally approved. A standard is approved by everybody. Okay. Sometimes the standards cannot be a cutting edge. I mean, I told on a scale of 100, standard will stop at 85 or 90. The remaining 10 is cutting edge always. So the standards and even guidelines, they define technology readiness levels and manufacturing readiness levels. In the design and manufacturing phase, standards are very good, insightful, and they are almost spot on. You follow the standard, you can design anywhere, build anywhere, and install anywhere. It works. Okay. The distinction between accepted, ready, and inspired. See, these three are very important. Okay. Helps to clarify different levels of compliance and innovation guidelines between standards and guidelines. When we say accepted, okay, standards will not always work on scale of 100. They stop at 85 because they want to go along with everybody. There can be some consensus, there can be some dissent. But standards by large is a consensus document. It is an industry consensus document. Anybody should be able to build it. Okay, that's why they stop at 85 to 90%. Accepted means successful recognition and integration of design, fabrication, assembly, and test methodologies. Anybody can do it. Okay, ready. Ready means general preparedness to use standard protocols effectively for cutting edge. Now, a new company or a new design company becomes a member of a standard association. They need time to assimilate the standards. So that is a question of
Yes.
ready. In 6
Yes.
months or 8 months, they become ready. Okay. Now, the third one, which is very, very important, is inspired. Creative or a conceptual application of applied principles, potentially in a modular or interoperable design. When you say inspired, generally it is a marketing term.
Yeah.
If I give an example, the amount of Swiss chocolate sold in third world country is more than Swiss chocolate manufactured in Switzerland. So
Yeah.
these are all inspired products. Okay.
Right.
So
Right.
people will
Right.
say, yes, we can meet it. I can guarantee you the performance, but I cannot give you 100% guarantee. It works,
Yeah.
but not guarantee.
Yeah.
It is inspiration. And but sometimes these inspired terminologies are cutting edge actually. They came out of the standard because standard bodies may not, it might have been not approved by everybody or whatever the reason, but it is always a cutting edge. Okay, it comes there. But going down the line within another 2 years, this becomes part of the standard. For example, the JEDEC lies a standard for component outlines, IC outlines. There are always JEDEC compliant outlines, which are called as registered outlines. If you use them, getting a second source, third source is very easy. But there are some components which are leading edge and cutting edge. They are more than JEDEC or they are less than JEDEC. But those components, if you use, they can be either cheaper or they can be the cutting edge. They may exceed the standard or they may not meet the standard. These people should understand. It may exceed the standard or it may not meet the standard. Then getting a second source, third source, educating people becomes a big problem. So as far as possible, this inspiration should be kept only at a marketing level. It should not get into your, either it should be standard ready or standard accepted. If we go inspired, we take a deviation, then we are in big trouble. Replication
Yeah.
becomes a very big problem. Okay.
Right.
And standards, example in multi-die systems, seamless design methodologies, design interoperability, and support for advanced packaging technologies. Why I'm telling this is this multi-die systems, advanced design, interoperability between design and manufacturing, and advanced packaging techniques. These are all your densification. And all these methods are required to run a AI machine. The AI machine will solve your problem. But to make a AI machine run, you have to make electronics. That's the beauty
Yes.
of AI. People are telling
Yeah.
AI may take away jobs, but as far as electronics is concerned,
It
AI
is
is the
growing.
biggest boost we have got.
Yes. Yes, sir. That is the biggest boost, and also the market is growing or exploding, I would say, on the
Yeah.
electronics manufacturing side of it. Yes.
Yeah, that's the advantage with AI, especially AI backend. AI
Yeah.
backend is a big black box. Very limited people are exposed. Maybe that is the cutting edge. I think
Yeah.
going forward, if one doesn't uh, adopt to AI, it's very difficult for them to come back to the track. I mean, this is
Right. Right.
my opinion,
Right.
and it is opinion of many experts whom I have interacted. So people are not afraid of AI now. People are,
Yeah.
just taken like a duck to water. Okay, thanks. Happy Easter to the audience.
Thank you very much, Mr. Amba Prasad. Excellent explanation of various slides on various, I would say, steps in the co-optimization of densification in electronics manufacturing. Very well explained, very comprehensive, but again at the same time very clearly given messages. So I hope everyone out there, they would definitely enjoy watching this show. If you are not watching right away on live show, because I know today is a Good Friday. A lot of people are on vacation. A lot of people here in the US, it's a long weekend. In many parts of the world, it's a long weekend, and so people are taking it easy. So you can always watch it on our YouTube channel, and I will also share this in all the LinkedIn groups as well. So with that, I think we are almost coming to an end to the show
Yeah,
of today's Mr. Ambaprasad. Thank you
yeah,
again, once again, for
yeah.
always,
Always. In
always,
fact, yeah. In fact, what happened is many standard companies, including with whom I'm associated with, they already started into advanced packaging and AI. Many standards which were dormant or which were some standards were ahead of the time, say 10, 20 years back. They were dormant actually, but now they are rewriting it and to aid advanced packaging, densification, co-optimization, and it's a very big collaborative process. Lot of mergers and uh, mergers are going to happen, especially in the EDA world. This is the next growth engine is densification, AI and artificial intelligence. Artificial intelligence
Absolutely.
to make your design and assembly easier, and as well as you require design and assembly to make AI machines. So this is a closed loop. Yeah, thanks again.
Absolutely, absolutely true. I agree with you, and I think there's a lot of interesting topics that we will be covering in the coming days. We'll be talking about definitely how AI plays a very important role in manufacturing activity. As Mr. Amba mentioned, that AI is one of the biggest boost for the electronics manufacturing, which is absolutely true because for having AI technology used, you need definitely the equipment to be manufactured, and those that happens through the electronics. That's, ladies and gentlemen, today's electronics manufacturing show from Global Electronics with Mr. Ambaprasad. We had a wonderful chat and densification. So we will come back next week at the same time with another topic on FMEA with Mr. Anil Raj of SFO Technologies from India, one of the largest electronics manufacturing service company for aerospace and other market segments. So we'll be having a chat with him on the FMEA. Stay tuned with us at the same time on same day. Again with your host Rajiv Kulkarni. Till then, take care of your health, yourself very good way, because health is wealth, as everybody says, and God bless. Thank you very much. Have a wonderful, happy weekend, which is a long weekend, and happy Easter to everyone. Thank you. Thank you, Mr. Ambaprasad.
Yeah, thank you.